Hi everyone, my name is Eleonora.isotta, and in this video talk, I will present the article Elastic Moduli, a tool for understanding chemical bonding and thermal transport in thermoelectric materials. This work comes from the group of Professor Alexandra Zevolkink at Michigan State University. So the work is focused on elastic properties, and in particular, we want to explore how these are connected with chemical bonding in materials, and how we can use this understanding to interpret trends in phonon transport, understand the anharmonicity of bonds, and also unveil details of phase transitions. So all of this understanding is important, for example, for the study of thermoelectric materials. So for those of you that are not familiar with the topic, thermoelectric materials are materials that can convert temperature gradients into voltage gradients via the Seebeck effect. And conversely, they can convert voltage gradients into temperature gradients with the Peltier effect. The most maybe famous example of thermoelectricity is a thermocouple. So when we put two dissimilar metals in contact and we place the two different junctions at different temperatures, a voltage will develop in the circuit, and by measuring this voltage, we are able to measure temperature. So that's how a thermocouple works, but applications in thermoelectricity go beyond the measurement of temperature. For example, historically, thermoelectrics were used for deep space propulsion. For example, most of the missions that we hear of, like Mars rovers like Perseverance or the other trips like Voyager, were actually powered by thermoelectrics. And in most recent years, there is research interest in trying to apply the thermoelectric technology for waste heat recovery and for cooling and thermal management. So in order for these applications to work better, we actually need materials that are high performance, and performance in thermoelectrics is quantified by the figure of merit, this quantity ZT here. So the higher ZT, the better the performance of the material. So the figure of merit is composed of the Seebeck coefficient square, the electrical conductivity and the temperature at the numerator, and of the thermal conductivity at the denominator, that is composed of an electronic and a lattice contribution. So it emerges very clearly that the lower the thermal conductivity, the better thermoelectric material will be. But of course, this needs to be done maintaining high all the parameters that are at the numerator. In order to be able to engineer the thermal conductivity materials, we need to understand what are the fundamental origin of this thermal conductivity. And that's why we have developed this work in which we try to understand the origin based on elastic properties. Okay, let's see some basics of elasticity. So the basic of elasticity is Hooke's law. So Hooke's law is very famous, and it basically tells us that if we have, for example, a spring with a mass attached to it, and we are pulling the mass with a force, then the force will be proportional to the displacement. In other words, if we apply twice the force, we expect to see twice the displacement. So of course, in materials, we do not have springs, we do not have mass moving, but we actually have a solid that usually is under equilibrium. So whatever was a displacement actually becomes a strain, which is a ratio of a microscopic displacement with the initial length. And whatever was a force becomes a stress, which is a force per unit area. But other than that, Hooke's law is pretty much the same. So it tells us that there's a proportionality constant between strain and stress. That is this C here. So there are some very simple cases that are called the engineering moduli, where the relationship between stress and strain is very specific, and we have very specific types of stress and strain. For example, we have the Young modulus that is defined when we have a tensile strain that it follows from a tensile stress. We have the shear modulus, that is the elastic constant that quantifies the deformation coming from a pure shear stress. The bulk modulus instead quantifies the change in volume that happens with an hydrostatic pressure. And the Poisson ratio quantifies the change in cross-section of our material when we have a tensile stress. So these are the engineering elastic moduli and define, let's say, very simple elastic cases. But in general, the problem is way more, let's say, complicated than that. So in order to define an elastic state, a random elastic state, we actually need a tensor. And this is because the stress that we can apply in a material will depend on the surface where it is applied. And for every surface, it will have three components in the three directions. So actually, the stress state is represented by a tensor notation. And the same is applied for strain. So stress and strain are both second-rank tensor. So if we think about a relationship between two second-rank tensor, this C here, that is our elasticity tensor, if you think about it, needs to be a fourth-rank tensor. So it needs to be, so if it is something that connects a 3x3 tensor with a 3x3 tensor, then this needs to be a 3x3x3x3 tensor. So a total of 81 coefficients. So this makes a lot of coefficients, probably not an easy way to use this tensor. But so what we do in real life is we simplify this tensor by using what is called the void notation. So the void notation makes use of the fact that these tensors are actually symmetric and writes down the tensor as what is called a pseudo vector, where only the, let's say, independent components of the stress tensor will survive. And then we do the same for the strain tensor. And we link the strain tensor with the strength tensor via only a simple elasticity matrix that this time is only 6x6, so 36 coefficients. But the elasticity matrix can be further simplified if we take into account the crystal symmetry of the material that we are studying. And this is because elasticity follows what is called the Neumann's principle. So the Neumann's principle tells us that the symmetry of the elastic response is going to be equal to the symmetry of the point group. So this means that when we have a certain geometry, a certain crystal structure, we expect the same type of symmetry to appear in the elastic constants. For example, lead telluride has a cubic crystal structure and has an octahedral coordination of atoms, meaning that every atom is surrounded by 6 nearest neighbors in this shape here. And if we look at the isosurface of the Young modulus, we can actually see that it has a symmetry that resembles the symmetry of lead telluride. In particular, we have the largest Young modulus along the same direction of the bond. Germanium telluride, for example, has a rhombohedral structure, which is a sort of distortion of the same structure that we saw in lead telluride. And in fact, the isosurface of the Young modulus looks like the one of lead telluride, but with a distortion. So that's because it follows the same symmetry of the crystal structure. Another remarkable case is that of polycrystals. So in most cases, polycrystals, when the grain size is sufficiently small, can actually be considered isotropic. Being isotropic means same properties in all directions, and therefore the isosurface for the Young modulus will be a sphere. The case of isotropic is particularly relevant. For example, in thermoelectrics, most materials can be actually considered isotropic when they are in polycrystalline form because grains tend to be very small with the production method we use. And in this case, the elasticity matrix becomes particularly simple because most terms go down to 0, and we're only left with C11 along this portion of the diagonal, C44 along the rest of the diagonal, and then C11 in these other elements here. But C12 in these other elements here. But C12 can actually be calculated from C11 and C44. So the problem is sort of bidimensional. We only have two parameters that are independent, C11 and C44. And this allows us to calculate any other elastic moduli, including the engineering elastic moduli, starting from the C11 and C44. And given the problem is bidimensional, knowledge of any two elastic moduli, in the case of isotropic samples, allows us to calculate all the other moduli by using these formulas here. Okay, but how do we calculate, how do we get these elastic moduli? So one way to get them is from experiments. For example, one of the most used and also most advanced method to obtain the elastic moduli from experiment is with resonant ultrasound spectroscopy, or RUS or RUS. So in this technique, the sample is clamped in between two transducers that emit over a certain frequency range. And then they will be able to pick up at which frequencies the sample resonate. So by building a model and by fitting the frequency dependence of the resonant peaks, we are actually able to understand the elasticity matrix, since these resonant frequencies, their frequency location will depend on the elastic properties and the geometry of the sample. That is something that we know. If we don't have RUS available, another way to get elastic moduli is from density functional theory, from DFT. For example, if you look up in materials project, in the website of materials project, you can find the elasticity matrix for a lot of compounds, like really a big number of compounds. One thing to really pay attention to is that DFT will calculate the elastic constants for single crystals. So if you have a polycrystalline sample and want to use the isotropic approximation, you cannot take the DFT elasticity matrix and plug it into your polycrystalline sample. Like, you cannot use it for a polycrystalline sample, but you can still use it. For example, if you have a polycrystalline sample, what you can do is you can do a Voigt-Royce-Hill averaging method, and you can get from this data here the isotropic averages. So you can still use the data, you simply need to go through this process here before you use it for a polycrystalline sample. And this process is described in this reference here if you want to go more in details. Okay, but then we wanted to explore what are actually the parameters at the base of this elastic moduli. And one strong contributor to elastic moduli is bond stiffness, in particular bond length and bond strength. For example, here we have compiled the trend of bulk modulus versus average volume per atom for a number of different compounds. So the average volume per atom is ultimately a proxy for the bond length. And as you can see, the larger the average volume per atom, the lower the bulk modulus is going to be. And this holds for a number of different compounds. This comes down to the Lennard-Jones interatomic potential. So this curve here describes the interatomic potential between two different atoms. So when they are sufficiently far away from each other, they will have no attraction, no repulsion, no interaction at all, and so the potential will be zero. As they get closer, attractive interaction will start to occur, and the curve will start having, like, the potential will start being negative. At some point, we reach a minimum, and beyond the minimum, in this portion of the curve, we will have repulsive interaction. So this will define a minimum that will be where the equilibrium distance is, and so where the atoms will have their, let's say, distance at equilibrium. So elastic moduli happen to be proportional to the curvature at the bottom of this interatomic potential. So this is what happens when we change the bond strength. So when we introduce weaker bonds, this is the way the Lennard-Jones interatomic potential changes. So we can see that for weaker bonds, the curvature at the bottom of this potential here will start to be lower. And so this means that we will have softer or lower moduli. At the same time, if we increase the bond length, this is the way the interatomic potential changes. So you can see that also in this case, increasing bond length will cause a decrease in the curvature of the potential at the minimum of the potential. So also in this case, increasing bond length means softer and lower moduli. So with this interpretation, you can probably guess what happens with temperature, because as you know, when we introduce energy in the form of temperature, atoms will start to vibrate, but given the shape of the interatomic potential, especially given this anharmonic part, they will start to oscillate with the average distance that will go larger and larger as we increase the temperature. And this is at the base of thermal expansion. So since we have an average bond length or an average distance in between the atom that becomes larger with temperature, we actually expect the elastic constants to actually decrease with temperature. And in fact, this is what happens for the Young modulus for some different compounds. So you can see that for all these compounds, we will have a decrease in elastic moduli with temperature. Then, of course, how much the elastic moduli decrease will depend on the compound. Okay, but let's explore how elastic moduli trend in between thermoelectrics. So this is a compilation of a series of thermoelectrics. So you can see straight off the bat that with temperature, we always have this decrease of elastic moduli. And we can see that different types of thermoelectrics will span a large range of, for example, Young modulus in this case. And one parameter that we can see again here that controls elastic moduli is bond stiffness. For example, among the stiffest thermoelectrics that we find are half Oislers, which have this covalent bonds and this tetrahedral coordination of atoms. Instead, among thermoelectrics with relatively low elastic constant, we have, for example, lead telluride, which has an octahedral coordination and rock salt crystal structure. And Zintal compounds, for example, are found having an intermediate values of elastic moduli, and this might be due to their crystal structure that has both some atoms that have tetrahedral coordination, so like the half Oislers, and some atoms that have an octahedral coordination, like lead telluride. So this might be the reason. At the very lower end of thermoelectrics, we have materials like tin selenide, that is a layered compound. So we have, of course, very soft bonds, soft moduli in between the layers. And on top of this, tin selenide has also this accordion-like shape of bonds within the layer that makes the structure very soft, even within the same layer. So yeah, you can see bond stiffness plays a strong role. Beyond bond stiffness, also bond length plays a strong role in determining the elastic moduli within the same crystal structure. For example, if we keep the comparison within half Oislers, we can see that if we go from titanium nickel tin to hafnium nickel tin, which overall has a larger volume per atom, since we have substituted titanium with hafnium, we will have lower elastic moduli. The same thing happens, for example, with Zintal when we go from antimony-based compounds to bismuth-based compounds that are larger in volume. And this trend in elastic moduli pretty much follows the trend that then we will find in lattice thermal conductivity. So it will go from very low to higher values like the half Oislers. Okay, but what is the intimate connection that exists between elastic moduli and lattice thermal conductivity? So one way to picture lattice thermal conductivity in a very simple way is the phonon gas model. The phonon gas model basically tells us that the lattice thermal conductivity is proportional to the specific heat, that is how much heat the material can actually uptake, the speed of sound to the second power, that is basically a measure of how phonon can travel, how fast phonons can travel in the material, and the phonon scattering time, that is the time in between scattering events for phonons. So this formula here is like a very simple picture and normally, if we want to be more precise, we need to take into account that each and every of these terms is actually frequency dependent. So a more sophisticated version of this model here is the Callaway model down here. So in the Callaway model, typically 3 assumptions are introduced when this model is used, for example, for large material computation. So assumption number 1 is that the group velocity of all phonons is approximated to be equal to the speed of sound, so the low frequency phonon velocity. The second assumption is that we usually consider the high temperature limit for the specific heat. The third assumption is that we consider as main phonon scattering mechanism happening in the sample Umklapp scattering or phonon-phonon scattering. So if we introduce all these 3 assumptions in this model here, the formula that we end up having is this one here. And this formula here has shown to behave very well in capturing the overall thermal conductivity behavior for a bunch of different compounds throughout a large span of lattice thermal conductivity values. So if we take a look at these 2 formulas that are sort of like a simpler and then a little bit more sophisticated picture of lattice thermal conductivity, what emerges very clearly is that a very strong parameter is the speed of sound here. That is to the 3rd power for this formula and to the 2nd power for this formula. So speed of sound can actually be calculated from elastic moduli, because for isotropic solid, for example, we can calculate the speed of sound simply is a direct function of the elastic moduli and the density. So it can be very straightforwardly calculated from elastic moduli. We normally calculate the longitudinal and the shear component, and then we can use one of these methods here to make an average and have an average speed of sound. So to get the speed of sound, one way to go is first of all to do resonant ultrasound spectroscopy measurement, get the elastic moduli, and then with the formulas get the speed of sound. Another way to go is measuring the speed of sound directly, for example, with methods like pulse echo or ultrasonic sound velocity methods. So we have seen before that elastic moduli decrease with temperature. So the same way, the speed of sound will also decrease with temperature. For example, here we have the speed of sound of lead telluride, and we can see that it actually declines with temperature as expected. So usually when this type of models are used, the temperature dependence of speed of sound is not taken into account. So usually the only temperature dependence here is this temperature here. So usually the speed of sound is considered as a constant. And this will actually introduce some errors in the prediction of lattice thermal conductivity because, for example, in red, this curve represents the thermal conductivity that we would predict if we actually take into account a temperature-dependent speed of sound, while in green, we can see the underestimation that we will obtain if we do not take into account this temperature dependence. But actually, predictions work pretty well, probably because there's another phenomenon that goes into this, because usually we make 2 assumptions. We make the assumption that speed of sound is constant, but we also make the assumption that heat capacity is constant. And heat capacity, instead of decreasing with temperature like speed of sound, actually increases with temperature. So their trend sort of compensate. And if we consider both of them constant, we end up having an error that is less than what we saw before. But we can still see that even though these 2 trends compensate, when we use the constant approximation, we still get some underestimation of the lattice thermal conductivity. And this is due to the fact that they will end up having different, they are elevated to different powers in this formula. That's why they don't completely compensate. So this points to the fact that if we have speed of sound measurements and if we have temperature-dependent speed of sound, this can actually help having better predictions of thermal conductivity. And this can be particularly important when the compound is anharmonic. So let's dive in a little bit in what anharmonicity is and what it means, and especially what is the connection with elastic moduli. So we have seen so far that one strong parameter that will determine the lattice thermoconductivity is speed of sound and how this is connected with elastic moduli. Now I want to show how also the phonon scattering time has a strong connection with elastic moduli. So usually the phonon scattering time is computed with this formula here that is called Mathiesen rule, where we consider the total phonon scattering rate to be a series of the scattering rates coming from all phonon scattering mechanisms. So one very important type of phonon scattering is umklapp scattering or phonon-phonon scattering. And this is particularly important, number one, because the effect is increasingly strong at high temperature. And for example, thermoelectrics are normally used at high temperature. The second point is that umklapp scattering is the only type of scattering that is present everywhere, even in perfect single crystals. So the scattering time coming from umklapp scattering is proportional also to this other coefficient here, gamma, that is called Grüneisen parameter. So the Grüneisen parameter is a measure of how anharmonic is our interatomic potential curve. So how much it will deviate from the harmonic trend. The Grüneisen parameter is usually mode specific. This means that every phonon mode will have its own Grüneisen parameter and is usually calculated from DFT by looking at the variation in frequency of this phonon mode when we have a variation in the volume of the crystal. So usually people, if they calculate it with DFT, will end up with a series of values for every phonon mode. And then they might consider a mode average if they want a unique parameter to compare different materials, for example. But DFT computation can be very expensive. Some other methods to estimate the Grüneisen parameter gained popularity. And these other methods sometimes are called thermodynamic averages. These thermodynamic averages often rely on elastic moduli. For example, one way to compute, to have an estimate of the Grüneisen parameter is through this formula here that we call the Leadbetter formula from the work from Varshny and Leadbetter, where they basically realize that the Grüneisen parameter will be connected with how much the elastic moduli will decline with temperature. So what's their temperature derivative? And in fact, the Leadbetter formula here takes into account the derivative of the elastic moduli with temperature. Another way to compute a thermodynamic average of Grüneisen parameter is the Poisson method that takes into account the Poisson coefficient of the material. And in this plot here, we have tried to compare these different methods for a series of different materials. So we can see that general trends in materials will hold. For example, germanium or diamond down here will be predicted by both methods as being relatively harmonic, so low Grüneisen parameter. On the other hand, materials like magnesium antimonide here is predicted by both methods as being highly anharmonic, so very high Grüneisen parameter. But you can see that the two methods deviate quite significantly. And in particular, we can notice that the Leadbetter method will end up with a larger spread in values. So in order to understand this, we took a look at the functional form of the Leadbetter and the Poisson method for calculating the Grüneisen parameter. And in blue here, we have the Grüneisen parameter from the Poisson method for a series of classical, let's say for a normal range of Poisson ratios. And in red, we have a trend, we have the trend of Grüneisen parameter with the Leadbetter formula for a series of regular temperature derivatives of the elastic moduli, in this case, the shear modulus. So what we can see straight off the bat is that the Leadbetter method will intrinsically allow to have a larger spread of Grüneisen parameter. On top of this, the Leadbetter formula does not depend only on the temperature derivative of elastic moduli. It will also depend on the volume per atom. So this gives the additional spread in values that we can achieve that here we have pictured as the red band. So all these, let's say the stronger dependence with temperature derivative, and additionally this other coefficient that the Grüneisen parameter estimate will depend on, gives overall a larger possibility, a larger domain of Grüneisen parameter that we can access if we use this formula here. A third method that is pretty common actually, and to have a thermodynamic estimate of the Grüneisen parameter is through the thermal expansion. And this method as well takes into account an elastic modulus, in particular the bulk modulus. So in this plot here, we have compared the Grüneisen parameter that we would obtain from these three thermodynamic averages and from DFT calculations for some very relevant compounds. So again, what we can see is that general trends will hold. For example, silicon will always be predicted as relatively harmonic, while materials like lead telluride will be predicted as anharmonic, high Grüneisen parameter. But we can see that there are significant variations method to method. So from this analysis, the emerging answer is that there's not a best method. If we want to compare different materials, probably we should use multiple methods and always have consistency in the methods that we use. So to conclude, I would like to show you how elastic moduli can be very powerful also in studying phase transitions. So why do we want to choose elastic moduli for phase transitions? So you might recall the Ehrenfest scheme that basically classifies phase transitions into first order and second order phase transitions. And this classification is based on where we see the discontinuity in properties with the evolution of the phase transition. So if we see a discontinuity in properties connected with the first derivative of Gibbs free energy, then we call that a first order phase transition. If we spot the discontinuity in properties connected with the second derivative of Gibbs free energy, then we call that a second order transition. So elastic moduli are relevant because they happen to be second order derivatives of Gibbs free energy, and this makes them particularly good in studying second order phase transitions. Here, I would like to give you some examples of how elastic moduli turned out useful in studying phase transitions. For example, germanium telluride has a temperature-activated phase transition from a rhombohedral structure to a cubic structure. And if we take a look at elastic moduli, we can see a sharp increase that basically will make it very easy to spot where the phase transition is and how the elastic moduli will be affected by the different crystal structure. This is another case that is a work from the group of Professor Zebel-Kink, where we have basically investigated this system composed of alloys of germanium selenide with silver bismuth selenide. So for intermediate alloying compositions, we have a structure that is rhombohedral at room temperature, and with temperature will evolve into a cubic structure. So even in this case, we can spot the transition very easily because we can see this sharp increase in elastic moduli when we transition from the rhombohedral to the cubic arrangement. A final case that I would like to present is this case here of alloys of germanium telluride with antimony telluride. So in this case, still from the group of Professor Zebel-Kink, they realize that this system here does not have the classical decrease in elastic moduli with temperature that we would expect that we have seen for a number of compounds, but elastic moduli actually increase with temperature. So this system happens to have a phase transition as well, where at low temperature, it has a rhombohedral structure, and it basically has some ordered layers of vacancies. What happens is that with temperature, these vacancies will start not belong anymore to ordered layers, but would actually start to disperse in the matrix. And this will make the structure be stiffer because we do not have this planes for shear anymore, but overall, this other arrangement will make the structure be stronger and stiffer. So with this, I would like to wrap up what we saw in this presentation. So first of all, we saw that for most thermoelectrics, bond strength is going to be a strong parameter that will determine the elastic moduli and in turn have an effect on lattice thermal conductivity. Then we saw that elastic moduli can be very powerful for the study of lattice thermal conductivity because they can give insights on both speed of sound and phonon scattering time, that are the two very strong parameters that will control the lattice thermal conductivity. Finally, we have seen a few cases where elastic moduli turned out very useful for the study of phase transitions. So with this, I would like to acknowledge my advisor at Michigan State, Professor Alexandra Zavolkink, and also Wanyu Pang and Srini Balodi that are co-authors in this work, and of course, all the Zavolkink group at Michigan State. So thank you very much for the attention. And of course, do not hesitate to contact us if you have any questions or comments. Thank you.